Now, so far we have been just manipulating one given signal. Now, what if we have bunch of signals and we have to work with multiple of those together and manipulate them simultaneously? For example, this happens in many circuits where you have, let's say, multiple capacitors or multiple components, and then you have to add signals which are coming from different components. Let's say you have a capacitor and an inductor. Now you have to get the signals as an output from both of these components, and then you have to add them together, you connect them together. If you're connecting them together, essentially the voltage across these two get added up, right, in whatever way. So what happens often in practice is you may have to manipulate signals while adding them up. So how to add signals, how to subtract signals? So given two signals, let's say I've been given x of t and y of t. So this is as good as saying that I have a circuit, okay, and the circuit is of this form. Okay, this is x of t, this is y of t, there is some gain and then there is some addition. Okay, so you have a circuit of this form. So I'm getting an output here. So how do I model this? Remember, what we are doing in this course is always, I'll repeat the statement again and again, whatever is going on in a circuit, we are going to model that using equations and analyze it. So this analysis helps us to find out how to design the circuit. Okay, so that's why we are going to do this analysis. So given some signal, let's say this is some x of t, another signal which is let's say y of t, how are we going to add or subtract this? We are just going to do this pointwise. So what does it mean pointwise? You take a particular point, see the corresponding value here, and then just multiply this value by a, multiply this value by b, and then plug in the same value here. Okay, so this signal probably becomes something like this. Okay, you just add or subtract pointwise. You really don't care about the rest of the signal. At a given time t, what is the value of x of t, what is the value of y of t, add them or subtract them, and then plug in the value at z of t. A simple example is that earlier we saw the step functions. If you remember, the step function is something of this form, and till 0 it is 0, after that it becomes 1. Okay, this is our step function. Okay, now from this we can get a lot of interesting other signals. So if you just multiply this by 2, then what do you get? So a step function just scaled in amplitude by 2 now becomes something like this. And then you subtract 1 from that. So what is 1? So if I have a constant, if I simply say that x of t is equal to 1, what does, and I ask you to plot it, how would you plot it? You say time t. So for no matter what t is, if I say what is the value of the signal at t is equal to 0, then according to this equation it is 1. What is the value of the signal at t is equal to 1? It is 1. No matter what the value of t is, the signal's value is always 1. It's a constant, which means it's just a straight line, right? So with amplitude 1. Okay, irrespective of the value of t here, x of t always says that it is 1. So which means no matter what the value of t is, it is always 1. Okay, so this is what we mean by a constant signal or a DC signal. Okay, now just subtract this from our step function, which is scaled. What would we get? So you're subtracting this for the negative values of time. This becomes pointwise subtraction. Remember, here it is 0, subtracting 1 from 0, which gives you minus 1. Okay, and then for positive values of time, you're subtracting 1 from 2, which gives you 1. Right, so this is what you get when you do this operation. In other words, this becomes our sine function. You can get the same thing in a different way also. All you have to do is just take u of t and then just add with minus of u of minus t. So what is u of minus t? So u of minus t is just time reversal of the signal, which is just moving everything on the left hand side. Okay, this is u of minus t, and then you subtract it. So if you're subtracting, whatever is the sign here, it just comes down. Now you just add these two and you get the sign of function again. So there are different ways of representing one given signal using other signals. So it is not unique, that we have to keep in mind. So it is not necessary that we can have a unique representation of a particular signal in terms of other signals. So if I give you y of t and then ask you to represent that in terms of some x of t, there could be multiple ways of this representation. There need not be one right answer, there could be multiple right answers. So depending upon what is your application of interest, depending upon what is your circuit, it might be useful or it might be easier if you represent it in a certain way. So if I can decompose my signal in certain ways, then it might be easier for me to analyze it more. So whichever is your application, then you have to know that, okay, for this particular application, if I can represent my signal, let's say my signal is x of t, and if I can represent my signal like this, let's say y of t minus y of minus t, then I'll be very, let's say it might be much easier to analyze this than analyzing something of this form plus some constant or something, right? So if you know this, then it might be just easier to just reverse it and analyze than to add something and so on. And this is just a simple example. Things might be even more complicated than this. So you need to know what actually would simplify your life. Whatever makes your life easier, follow that decomposition. And we have another example here, the rect function. So do you remember what is the rect function, the rectangular function? It is 1 from minus half to plus half, right? A very nice way of representing this using the step function is to use our time shifting method that we have learned some time back. So shift the step function to the right. So if you shift the left function to the right, step function to the right, what would you get? You get something like this. How would you shift it to the right? By adding a time parameter or a shift parameter that is negative. So this is u of t minus half, okay? And then get another one which is shifted to the left. So what is shifted to the left? This step function, and if it is shifted to the left, remember the shift parameter is positive, it will be like this. Now just subtract one from the other. So in this region they are exactly the same, so they'll cancel out. So all you're left out with is this portion, which is minus half to half, which gives you the rectangular function here. So this helps us to represent one signal in terms of the other. Now let's say you know how to analyze step functions completely. You've learned that completely. But you don't know how to analyze rectangular functions. You need not worry, because any rectangular function that you encounter, now you can rewrite or decompose that in terms of the step functions, and then just by using the step function analysis, you can completely analyze rect function. So this is a theme that we'll often use in this course, where we'll decompose any given signal in terms of something that we already know how to analyze. So if I know completely how to analyze, how to understand the step function, I can take care of all kinds of rectangular function. You can now shift this rectangular function, you can scale this rectangular function. So if I ask you to represent rectangular function of, let's say, minus 2 plus 5, take this as an exercise and represent that in terms of step functions. You can do this, right? All you have to do is just find out the corresponding step functions here. I can scale this by 3. I can still find out what is this corresponding step function. So you can represent any rectangular function in terms of step functions now. And then let's say you've mastered how to analyze a step function, then which automatically means you've also mastered how to analyze rectangular function. So this is what we will do in a major part of this course, we will take one particular signal, and I will tell you later what the signal is, and we will master how to analyze that signal. And whatever be the signal that you encounter later, you will always try to decompose that signal in terms of the other signal, and then say that, okay, I will now analyze the signal in terms of this decomposed version. This is a very interesting technique that we will use. So, if you know something, always decompose anything new that is given to you in terms of whatever you know. Okay. So, this is also something we often do in practice in real life also, right? If you know only addition, then you break down every multiplication operation into addition, and then you just try to do addition and then find out what the answer is. That's what we'll do in this. We'll break down anything that is new to us in terms of something we already know, and then analyze using that. Okay, let's see once again some interesting examples here. So, x of t here is given, and then we are now asked to express x1 of t in terms of x of t. So, I should use x of t or multiple components of x of t. I can use different components, like I can say that I'll have some c1 times x of a1 t plus b1 plus some c2 times x of a2 t plus b2 and so on up to some cn x of a n t plus bn. So, what we are asked here is to decompose this given signal in terms of x of t itself. Okay, that's what we are asked. So, let's try to do how can we decompose this. Let's try to see how to decompose these things. Okay. The first thing that we can immediately observe is we have this shape here, and that shape directly comes here as such. Okay. And this width here, critical time points t0 and t1. Okay. So, we will break down this signal into two parts. We will say that, okay, I will identify first how to get this portion. Okay. And then we will identify how to get the other portion. Okay. We will break down this into two different signals and then try to get each one of them separately. Okay, let's first try to find out this. That's easier. So, it is basically x of t, but shifted to the left by how many time instances? 0 here has become -1. So, which means it's shifted to the left by one time instance. So, this portion we can obtain by getting x of t plus 1. Remember, shifting to the right is minus and shifting to the left is plus. Now, how to get the other portion that we have here? Okay. So, the first thing that you can see here is the origin which was here at 0 has come to 1. Okay. And here whatever was at 1 has come to 0, which means there is a shift of origin, and then there has also been a time reversal. So, there is an A and B involved. So, in order to find this component, you have to find out what is A and we have to find out what is B. So, let's use our good old formula and then see what happens here. So, T1 minus T0 is 1 minus 0, gets mapped onto 0 and 1. So, which means A is minus 1. Okay. So, once we know A is minus 1, we can figure out B easily. B is minus of A V0 minus A is minus 1. And what is V0 here? V0 is 1 because the origin got shifted to 1. So, this is 1. So, this is 1. So, which means the other signal that we are looking for is x of minus t plus 1. Okay. So, the total signal x1 of t can be now written as x of t plus 1 plus x of minus t plus 1. Alright. Now let's see how to get the next signal. So this is a rectangular signal. This is interesting. Now remember earlier we represented rectangular in terms of step function, but now we have something which looks like half of a triangular function, and then we are saying we'll represent rectangular function using that. So like I said, there are many possible decompositions. This is one of the decomposition. Now how to represent this? So I'll give you only one of the ways possible. There are many ways. You can come up with many different ways of representing this. So you can think of this, take this as an exercise, maybe try to come up with a different decomposition than what we are discussing here. Now the way that I can think of one way to get the rectangular function is to get a signal of this form. Okay, I'll get something like this. Okay, and then I will just time reverse it. Now add these two things together. If I add these two things together, then I'll get a rectangular function. So I have to find these two components. So x2 of t. Now let's focus on getting this one. How do I get that one? So there has been a scaling done here because whatever is just one time instant width has become 2 time instant width. So there is a scaling factor, and the origin also has moved to -1. So there has been both scaling and there is both shift of origin. So let's first find out what is the scaling factor. It has stretched. Because it's stretched, now the magnitude of A should be less than 1. Let's see if we are getting something which is less than 1. Okay. So 1 minus 0, whatever is at 1 has now gone to or staying back at 1. That's good. Whatever is at 0 now has moved to -1. Minus of -1 plus 1. So A is half. Our intuition was right. Now what is B? So B is minus A times wherever the origin has shifted. So the origin has shifted to -1, right? Whatever was 0 here has now gone to -1. So this is of -1. So which means this is B of. This also makes sense because the signal has moved to the left. The signal has moved to the left, then the time shift parameter should be positive. So we got positive. So the first component that we are looking for is t by 2 plus half. Now the other one that I want is just time reversed version. So I don't have to do anything, just take the same thing and put a minus in front of my t here, because all I have to do is just time reverse it and nothing else. Okay. If you want, you can just do the same operation of finding out A and B. You will get A to be negative and B to be still the same. So just a time reversal, which is shifting or reversing the sign of t, is sufficient. So this is how we can decompose the signal x2 of t in terms of x of t. Let's move on to the next one. We're getting a little more complicated signal. How to find this x3 of t? So once again, we have to decompose this into things that we already know. Okay. So one way is to see that there are many ways. Okay, you can do it in a different way. I can do it in a different way. So I'll do it in a way that I can think of right now. Okay. So one way is I can use the rectangular function that we just found out, -2 to 2, but then see that it has now stretched. Here it was -1 to 1, but now we have -2 to 2. So this is a rectangular function that is stretched. I can do this and add this with this component, which is now 1. Okay, this is 0 to 2, and then add this with. So now I've decomposed this into 3 signals. And then I'm going to add up all these 3 signals to get whatever that is required. So x3 of t is, as you can see, first thing is the rectangular signal, but it is stretched in time, which means it is x2 of t by 2. Okay. What is x2 of t by 2? If I want to represent that in terms of x of t, it is x of, the time parameter is the only thing that is getting scaled. So t by 2 by 2, t by 4 plus, the constant remains the same because that is not divided, plus x of minus t by 4 plus half. Okay, you can check this if this is true. Okay, take this as an exercise, check if this is true. Plus, now we have to figure out how to get this component. As you can see, once again, it is just a time stretched version. The origin here still remains the same point here. So b is 0. That is great, which helps us to get the signal easily. So b is 0. Only thing is there is a time stretch, and it is now getting stretched by 2 times. So if the stretch is twice, all you have to do is divide time by 2. That's all. As simple as that. And to get this component, it's just the time reversed of the previous. Easy. So although the signal looked complicated, the decomposition looks quite simple, right? So if you know how to analyze this signal, you can analyze everything else here. All the other complicated looking signals could be analyzed just by knowing how to analyze this x of t. That's the beauty of knowing how to manipulate signals. Okay, now let's take the final signal x phi of t here. X4 is missing for some other whatever reason. Okay, once again what we'll do is we'll decompose this into 3 different components. I'm sure by now you would have guessed what are the 3 different components. The first is a rectangular function, but then this is squished. This is between minus half to plus half. Okay, and there is another one which is between half to 3 by 2 and minus 3 by 2 to minus half. If you add these 3 components, you get what you're looking for. So the first one is a rectangular function, and it's a squished rectangular function. So whatever was here x2, you just squish it. So if you're squishing it by twice, you have to squish it by twice because 1 becomes half here, right? So all you have to do is multiply t. So how do you express x of 2t in terms of x of t? So all you have to do is just multiply wherever t comes, replace that with 2t. That's all. So in this case, you have t by 2, just replace t with 2t and you're done. So you just get this plus x of minus t plus half. Okay, first component is done. Let's find the next 2 components. So this component here, the width has not changed, meaning whatever is here has come as such. And similarly here, whatever is here is same as this. So if you look at this component, then it is the same as x of t. Only thing is the origin has been shifted, nothing else. So a is 1. So you don't have to worry about the scale parameter because the scaling is equal to 1. There is no change in the scaling. So whatever is the width 1 here is same to 1. All you have to worry about is the shift. It has moved to the left. So the origin was at 0, but then as you can see here, the origin has now moved to minus 3 by 2. Okay, so moving to the left means having a positive time shift parameter. So this is as good as saying this is x of t plus 3 by 2. Okay, and then how do you get this component? Keep in mind it's just the time reversal. Okay, so you just reverse whatever is here in time, you would get this component you're looking for. So the other component is just x of minus t plus 3 by 2 and you're done. You get the signal what you're looking for. Okay, so this now gives us a nice hands-on on how to decompose different signals in terms of one known signal, how to find out the components. This will help us in analyzing signals later in this course.